All right, guys. Same game with I'm rolling the dice. Very exciting, this gambling game. I hope you're enjoying it. It's very thrilling. What if I double the money instead of subtracting $1? So I'm gambling. I'm rolling a die. Roll 1 or 6, you win $20. Roll 2, 3, or 4, or 5, you get 0. So I multiplied these by 2, right? And forget about paying. I'm just going to consider only the winnings again. So, I mean, we could look at it with both of them, and we could, where you're actually multiplying by 2 and you're subtracting 1, and I think we know what we should have to do with that. But for now, the chance of getting 0 is 4/6, and the chance of winning $20, because we double it, is now 2/6. Find the expected value. Well, the original expected value was $3.33, I believe. I'm looking at my notes from before. And the original standard deviation was $4.71. That's the original, the OG, if you will. Okay, so find the expected value. Here we go. Mu of x is equal to the 0 times, not 0 times. That's so dumb. Parentheses, 0 minus the mean. I'm trying to find the mean. No, I was right in the first place. Guys, just awful. It is 0 times 4/6. There we go. There you go, Larson. You got it. And then 20 times 2/6. Seriously losing it. 0 times 4/6 is just 0. 0 times, let's see, 6 times 20 is 122 over 6. Did I do that right? 20 times 6 is, 120. Sorry, 120. You know what? I'm going to hurt myself. Seriously, I'm going to injure myself if I try and do that in my head. I don't even know why I was trying. It's $6.66. And it's Thursday. Okay. If I play this many, many times and I keep track of how much I win and how much I lost, there'd be a bunch of zeros and a bunch of 20s, and the average would be $6.66. You know that, right? Find the standard deviation. Okay. That's going to go sigma of x equals a big giant square root, but I'm not going to go too far. That's not last time. Got burned. I'm going to go 0 minus the mean, which is $6.66. I'm going to square that and multiply it times 4/6. That's its probability. And then, I should have made it longer. This is going to be 20 minus $6.66. That's squared, and it's times 2/3, even a little bit longer. And then I'm not going to try and do that in my head. I'm not even going to pretend to bring the calculator out here. That's 2/6. You see, I'm just bad with math right now. I was upgrading a lot yesterday. Anyway, I'm not even going to pretend that I'm putting this in the calculator. I'm looking at my notes where I did it last year, and it is $9.42. Go ahead, judge. Judge all you want. Judge. I don't care. Now, let's compare these with the originals. I multiplied by 2. You multiply the mean by 2. And hey, look at that. You multiply the standard deviation by 2. Didn't we find out before that when we multiply every x value by a number, we multiply the mean, and we also multiply the standard deviation? Okay, so let's sum that up. Compare 2 means and 2 standard deviations. When you multiply, when you go and multiply the same number to all x values, you can just multiply that number to the mean and get your new mean. You can also multiply that number times the standard deviation, and you get the new standard deviation. Right? Didn't we already know this stuff? I mean, I don't think you would have come up with it on your own just looking at the charts. But now that we've gone through and do it, it's got to sound familiar to you, and I think you knew this. So look, I'm going to summarize everything right here. The linear transformations. The reason we call these the linear transformations is I'm going to write it like this. You ready? A plus bx. To the x, I multiply x by b, which in this case was 2, and I add, and maybe after I multiply, or if I don't have something I'm multiplying, I add a, which we added -1 on the last page. Well, if I put a y in front of that, isn't this a line? If the only 2 mathy things I'm doing are multiplying times x and adding, that's a linear thing. Now, if I was squaring something, it wouldn't be. It'd be a parabola, right? But the only 2 things I'm doing is adding and multiplying. That comes out to be a linear thing. So we call these the linear transformations. Adding something to every x value and multiplying something to every x value. Adding and or multiplying a number to each data value is referred to as a linear transformation because in the equation y equals mx plus b, which you're familiar with from algebra, the only math you actually do to the x value when you substitute something in for x is that you multiply and that you add. Of course, dividing and subtracting come out to be the same thing, right? Bullet point number 1, this is for pluses. If you add or subtract the same number a to every x value for a discrete random variable. This works for continuous random variables also, by the way, so I didn't put either one of those. The expected value, which we also know as the mean, right? The expected value, I'll put in parentheses, mu of x, changes by adding a, or subtracting a if you subtract it. But the standard deviation, sigma of x, does not change. Oh, I'm going somewhere with this very soon. Variance is going to come into play, people. You don't even see it coming. Bullet point number 2, that's what happens when we multiply. If you multiply the same number, b, the same number b, times every x value for a random variable, the mean changes by getting multiplied by b, and the standard deviation, sigma x, changes by multiplying by, you ready for this? Are you ready for this? Absolute value of b. Now, why would I write something so silly like that? Because we square everything when we're making standard deviations. Standard deviations are always positive. So if we happen to be multiplying for some crazy reason by a -2 instead of a +2, we don't want to come up with a standard deviation that's negative. It just doesn't make any sense to us, because standard deviation is a distance on the number line describing how spread out the data are. So negatives don't make sense. So we sneak in a little absolute value there just so we can be sure we sound like we know what we're talking about. Okay, I'm going to start you off on the next page, but I'm not going anywhere with it. I think I'm about wrapped up for today. I'm clearly not very smart. I graded too much. I hurt myself. I don't think my brain's working quite like it should, but at least I'll start this for you. Combining random variables. Well, now it's not just about 1x as a random variable, like how much you get off of this dice rolling thing. Well, now we're going to make a new random variable. I'm going to call it W for today, where you take the winnings from x and some other game you played and you add them together. Now we're combining random variables. We got some new rules to come up with because we've never looked at that before. Combining random variables means to get the random variable for x from the chance process, whatever the chance process was for x. In our case, it was rolling a die. Very exciting gambling game. And then get the random variable for y from its chance process, and you either add the two results or you subtract the two results depending on the context of the problem. If we're gambling and I'm seeing how much I won from this game and how much I won from that game, I'm probably adding those two things together, right? But there are scenarios, and we'll see one shortly, where you would actually want to subtract the two random variables. Okay, so of course, if I'm going to do another gambling, and I did this thrilling thing where I rolled a die, you got to know I'm about to flip a coin, right? So now I'm going to gamble at 2 games. I'm going to combine my winnings. The first, here we go, game 1. I'm going to pay $1, and there it is. I'm heroically going to flip a coin. If it's heads, I triple my money. If it's tails, I lose that $1. X is going to equal the net gain. So look, if I lose my $1. If it's heads, I triple my money. I paid $1 and I triple my money, so I get $3. Now, why isn't 3 there? Because I paid $1 to play. You see what I mean? I give you $1, I triple my money, you give me $3. I really only walked away with $2 extra. True? True. Now, these are both 1/2. Yeah? And down here, game number 2, I'm going to play the roll the die game. I pay $10 to do this. If I get a 1 or a 6, I double my money. So I would end up getting $20, but I paid $20. And if I got, I paid $10. If I got $20, I really only gained $10. If I lose, I lost $10. Now, this isn't 1/2 and 1/2, of course. This one is, you got a 4/6 chance to lose this $10, and you got a 2/6 chance to double your money and end up getting $20 back out of this deal. So I'm going to tell you what we're going to do tomorrow. I am going to give you a few homework problems on just the linear transformations, just adding and just multiplying. But I'm going to tell you exactly what we're going to do. We're going to find the mean of this. Then we're going to find the variance and the standard deviation of this flip the coin situation. Then down here, we're going to do an expected value for the average you would expect to get if you played this over and over. We're going to find the variance, and we're going to find the standard deviation. And then, over the next couple of pages, we're actually going to add them together and see what happens. Now, we'll try our little trick of what we think should happen. And then we'll actually break down all the different ways this could go. That one plus this one, or that one plus this one, or that one plus this one, or that one plus this one. There'll be 4 different options. We'll find the probabilities that go with them, and then we'll get a new distribution. We'll find the mean and standard deviation of that distribution, and we'll see what kind of rules we come up with, okay? I know that was a lot of words in a little time, but that's where we're heading. So tonight, your homework, I'm going to put it on Sapling. I'm going to just pick a couple of them from Sapling so we can get used to using that website again. And then plan on tomorrow us finishing these notes. All right? Have yourselves a good day. See ya.